Hello, this is Yusuke Koda in Kyoto University, and in the second video, I would like to extend multimodal split learning for multiple camera case. This is also joint work from Mehdi Bennis professors and Jihong Park and professors in Kyoto University. Okay, here's an outline, and we would like to mention two key takeaways. We consider multiple camera cases in this video, and we answer the following two key questions specific to the multiple camera cases. And first question is how we can make a different frame rate in distributed cameras compatible to each other in a communication and energy efficient way. And the answer is that we would like to propose a manifold mix-up interpolation, that is, interpolating features in upper layers. Okay, and the second question is how we can design a split learning scalable to the increase in the distributed cameras. In the split learning, upper layers input size increases as distributed camera increases. If you'd like to combine images from distributed cameras, and we would like to provide the answer of manifold mix-up aggregation. This is an average-based aggregation. Can be realized scalable split learning in terms of the energy efficiency. Here's an architecture of multimodal split learning in two camera cases. We consider two cameras that has a different field of view. Okay, and in this architecture, the key point is this feature aggregation method that aggregates two distributed camera image features. And the reason is that this different field of views images essentially non-IID, right? So that prohibits from aggregating layer parameters as federated learning. So we employ feature aggregation in the upper base station procedures. Okay, and this aggregated feature is combined into receive power features in the fully connected layers and output future receivable powers. And given the multimodal split learning in the two camera cases, the first topic is to answer how can we make a different frame rate compatible to each other in a communication and energy efficiency manner. Before we take off our proposal, I would like to mention a problem providing two naive baselines, that is thinning and mix-up. In both cases, we consider two camera cases. The one has higher frame rate and the other has lower frame rate. So in the camera B, is basically lacks the images corresponding to the other one here. In thinning, the camera A discards this redundant image and feeds the remaining images into convolution layers and makes the number of images compatible to the other one. In this case, communication and energy efficiency is better because the input size becomes smaller, so this makes the convolution layers recurrent layers computation costs smaller, and communication cost is better than the other baseline because of the smaller payload size. But you discard the essential feature images, so the prediction accuracy may be poorer than the other baseline. And the other baseline is a mix-up that interpolates image features, taking, say, linear interpolation. This outperforms the other one because this interpolates features may essentially helps to enhance the prediction accuracy, but communication and energy efficiency becomes poorer than the other baseline because of higher payload size and higher input dimension. Okay, given these two baselines, we propose the base station side manifold mix-up interpolation. The idea is simple. We take interpolation in the base station side. So that is, we interpolate image features in the base station size. This achieves intermediate communication and energy efficiency because as mix-up, we don't gain the raw image in the camera speed side. And hopefully prediction accuracy is better than the thinning and better than the mix-up that is evaluated from the next slide. Here, this is an experimental setting. We deploy two cameras, camera A and camera B, that has different field of view, and we predict ratio power 500 milliseconds ahead. Here, this is the result of accuracy and uplink cumulative communication costs, and you can find out two things. This green line is thinning, and this is a mix-up. And this is a manifold mix-up, our proposal. Okay, and you can find out two things. First, this thinning achieves fastest convergence due to the smallest payload size. But this mix-up and manifold mix-up achieves better prediction accuracy, slightly better prediction accuracy than thinning. And the key point is that comparing these two cases, the manifold mix-up achieves fast convergence due to smaller payload size rather than mix-up cases. So as expected, this manifold mix-up presents an intermediate result in terms of communication costs, but better performs thinning and comparable to the mix-up case. This is a detailed comparison in terms of RMSE and uplink communication costs and energy costs. And as I said before, in manifold mix-up performs better prediction accuracy compared to thinning and comparable to the mix-up. But manifold mix-ups exhibits an intermediate result in terms of uplink costs and energy costs, and actually better than the mix-up case. Okay, let's move to the second topic. In this topic, we answer how to design a multimodal split learning scalable to the increase in the number of distributed cameras in terms of energy efficiency. Okay, first I'd like to mention the problem from increasing the number of cameras. In the set experiment, we employ the concatenation in the aggregation feature aggregation method. That is, say, camera A is image and camera B is image. And in this case, as number of cameras increases, the full layer size becomes higher, and that means the energy consumption and memory bandwidth becomes higher as well. Okay, this is our proposal of manifold mix-up based feature aggregation in distributed cameras. The idea is simple. In this case, we average image features into one image and feeds to fully connected layers. In this case, the size of image is constant regardless of the number of cameras, and the size of fully connected layer is constant as well, and that contributes to the memories and energy consumption. And that's what our proposal looks like. And we know that this averaging based feature aggregation is provided in the literature, but we would like to emphasize that this averaging contributes to not only prediction performance but also the energy consumption and memories in the split learning context. Okay, finally, we would like to make performance comparison in terms of RMSE and size of fully connected layers and energy costs between just concatenating image features and manifold mix-up image feature aggregations. And in the manifold mix-up based interpolations, the RMSE is competitive in both cases, but the energy cost in base station becomes smaller. Okay, so this finding shows that you can enhance the energy cost in base station without sacrificing RMSE by changing the image feature aggregation method from concatenating to manifold mix-up aggregation across cameras. Okay, here's a summary. In this video, I answered the following two questions and provided the answer. The first one is to answer how can we achieve makes this different frame setting compatible to each other in a communication and energy efficient manner, and provided manifold mix-up interpolation. The second is answer how we can design a split learning scalable to the increasing the number of distributed cameras and provided the manifold mix-up based aggregation that is image averaging aggregation. That's all for this video. Thanks for watching.